This is the next video in the chapter on stoichiometry of chemical reactions. We have just finished learning about redox reactions, and now we're going to introduce a special set of rules to help us balance these equations because they're a little bit trickier than normal equations to balance. So we have a special set of rules that we use for these, because we have to take into account how many electrons are transferred. You may not see those in the balanced reaction because ideally the number that's passed from the oxidant to the reductant is the same and they cancel out. So we have a special procedure for balancing redox reactions to ensure both sides have the same number of electrons. So just like we need to have the same number of oxygens on both sides and the same number of hydrogens on both sides, we also need to have the same number of electrons on both sides. They will simply cancel out, so you just won't be able to tell if you've done it correctly. So there is a process for doing this, and you will need to memorize this. This is not something that will be given to you on an exam. Most of the time, we balance a redox equation in an acid or in a base because we need to have some ions floating around. And the best practice is to balance your reaction in an acid first. And then if the problem asks you to balance it in a base, there are a couple of extra steps that we add on to the end. So the way we're going to do this is we're going to pretend it's an acid first, whether it is or not. And we will write out the two half reactions. So we'll find the oxidation numbers, we'll identify what's being reduced and what's being oxidized, and we'll write those half reactions like we did in the previous video. Then we will balance each of the half reactions separately so we can figure out how many electrons are transferred. And we're going to do that in stages. So we're going to start with all of the elements except oxygen and hydrogen. So any of our metals or any other elements that are present. Then we'll balance the oxygen. And instead of balancing the oxygen by adding a coefficient in front of things with oxygen, we're going to add a new compound. We're going to add water to make up for any missing oxygens. And then we are going to balance the hydrogens last. And instead of adding a coefficient in front of anything with a hydrogen, we're going to specifically add in H pluses, because H pluses are present in acidic solution. Finally, we'll balance our electrons. So we'll look at the charge of each of the components, and we will add electrons as needed to one side until both sides have the same charge, because we have to balance the charge just like we balance each of the elements. And then once we're done, we will combine the two half reactions together, but we need to combine them so that the number of electrons transferred is the same for both of them. So we usually need to multiply each of the equations by something to equalize the number of electrons. And finally, we will add the half reactions together, cancel out the electrons, and we'll be finished. So it sounds like a long process, especially when the camera is out of focus, but it's actually not as long as it sounds in practice. When you are doing a problem in basic solution, you will do the entire acid solution, and then you will do two additional steps at the end. We want to get rid of the H pluses that would be present in acids and replace that with an OH minus that's present in a base. So we're going to add a certain number of hydroxides to each side of the equation, specifically the same number of hydroxides as the number of protons that is already present. And we're going to do that to both sides, because we can add whatever we want to a reaction as long as we do it on both sides. That is how math works. And then we're going to be sneaky, and we're going to say, just like in an acid-base reaction, we can combine a hydroxide and a proton to give us a water. So every time we have both of those present, we can write that as a water, and then we can cancel those out to have a reaction balanced in base. I know this sounds like a lot, a whole new set of rules that you have to have memorized, but let's do a couple of examples, and I think that you'll see most of it is pretty straightforward, as long as you remember to save oxygen and hydrogen for last in the process. Take a minute and write down the example, and then we'll see if we can balance this reaction in acid and then in base. So our reaction is hydrogen peroxide, or H2O2, aqueous solution, plus this polyatomic ion, which is called manganese. And that produces manganese 2+ ion and oxygen gas. So according to our steps for acidic solutions, the first thing we need to do is write both of the half reactions, but the secret unwritten first step is we have to figure out what's being oxidized and what is being reduced in order to do that, in order to write the reduction half reaction and the oxidation half reaction. Let's see what we can find out. So we have some rules about oxidation numbers. And I see that we have rules about hydrogen and oxygen. We have rule number 5 says that hydrogen is +1. And there are 2 of those, which makes +2. And rule number 6 says that oxygen is -2, but I see that both of those cannot be true. So we break from the bottom and we change the rule for oxygen to be an oxidation number of -1. We don't have a rule for manganate, so we'll have to figure that out. Oxygen is usually -2 when there's not another rule contradicting that. There are 4 of those, so the total is -8. And we see that the total of whatever manganese is in this compound plus -8 has to equal the overall charge of that molecule, which is -1. So something -8 equals -1, so manganese is going to be +7, which is a very high oxidation number. Over here on the right side, manganese 2+, there's only one element in that compound and the total charge is +2. So manganese has an oxidation number of +2. And oxygen is the only element in this compound. The total charge is 0. So oxygen's oxidation state is 0. Now that we know all of them, let's see if we can find the oxidation and reduction. So hydrogen is only present on one side right now. Oxygen is going from -1 or -2 to 0. So that means that the oxygen is being oxidized because that oxidation state is increasing. And manganese is going from +7 to +2. So the manganese oxidation state is being reduced. There are a lot of oxygens present in this problem, but the oxygens will eventually work themselves out after we finish balancing it. So now we know what's being oxidized and what's being reduced. So we'll copy everything that's involved in this reduced section over here into our reduced line. We've got our MnO4- and our Mn2+, everything with manganese in it. And then down here in our oxidation zone, we'll include everything else. So our H2O2 and our O2. And notice I'm leaving a lot of space here, so we have room to add terms as we balance. Okay, so checking our rule again, write both half reactions. Check. We have done that. Rule number 2, balance all the elements except for oxygen and hydrogen. So our only element other than oxygen and hydrogen is manganese. And we can see that there's only one manganese for each of them. So there's nothing else we need to do there. Step 3 is balance oxygens by adding water. So there are 4 oxygens on the left side in the reduction reaction and none on the right side. So instead of multiplying something as we would do when we were normally balancing, we have to add a new term that contains oxygen. So we're going to add 4 waters. So that gives us 4 oxygens on each side. And for our oxidation half reaction, we have 2 oxygens and 2 oxygens. So that is set. For our step 4, we need to balance any hydrogens by adding H+, by adding those protons. In our reduction half reaction, there's no protons on the left side, and we have added 8 protons on the right side, 4 times 2. So in order for those to be the same number, we need to add acidic protons on the left side. So there's 8 in both. And our oxidation half reaction, there's 2 on the left side. So we need to add 2 on the right side. Check. That's the wrong paper. Here we go. Step 5. We're going to balance the charge by adding electrons where they're needed. So by balance, we don't mean that we need to get the charge to 0 on both sides, although you could do that. What we're trying to do is just make the charge on each side the same. So we'll find what the charge is on the left side of our reduction reaction. We have 8 positive charges from these H's. We have 1 negative charge from this manganate. So that means we have a charge of +7 on the left side. And on the right side, we have a manganese 2+ and a water without a charge. So there's a charge of +2 on the right side. So in order to get from +7 and +2 to be the same, we only have electrons to add, and electrons have a negative charge. So we're going to add electrons to the more positive side so that both sides equal the lower number of +2. So if I add 5 electrons to the left side, that means that both sides will now have a charge of +2. For our oxidation half reaction, we have a charge of 0 on the left side, and we have a charge of +2 on the right side. So we need to reduce the more positive side by adding electrons. So we'll add 2 electrons to the right side. All right, so that's the hard part. Now all we have to do is multiply each of those half reactions by the appropriate coefficients to equalize the number of electrons, because the same number of electrons should have been passed from the oxidant to the reductant. And so we can see that there are 5 electrons in the reduction half reaction and 2 electrons in the oxidation half reaction. So to make sure that we have the same number, we need to multiply them by another number to reach the least common denominator. So the least common denominator of 5 and 2 is 10. So we can multiply the first one by 2 and the second one by 5 so that they both equal 10. So I'll write those over again. So we're going to take the first reaction times 2. 1 times 2 is 2 MnO4 minus. 8 times 2 is 16 H plus. 5 times 2 is 10 electrons. 1 times 2 is, 2 manganese, and 4 times 2 is 8 waters. Okay, and now we need to multiply our other one. 5 times 1 is 5 peroxides. 5 times 1 is 5 oxygens. 5 times 2 is 10 protons, and 5 times 2 is 10 electrons. Okay, so that was our step 6, multiplying. And so now our final step is to add everything together and to cancel out any terms that are present on both sides. We'll put a plus sign and a sum. We'll add them together to get the total. We just want to make sure we don't lose any of the terms. So we've got 2 MnO4 minus plus 16 H plus 10 electrons plus 5 H2O2 from both of the left sides. And then from both of our right sides, we have 2 Mn2 plus 8 H2O plus 5 O2, and we're out of room, so we'll have to start writing it on the next line, plus 10 H plus 10 electron, and then we'll look to see if there's anything we can cancel. We should be able to cancel the number of electrons, 10 on the left and 10 on the right, because that was the whole point behind multiplying these. And it looks like we have something else we can cancel. We have 16 protons on the left side and 10 protons on the right side. And just as if this was 16x and 10x, we can collect those terms all on one side. So we can collect 6 of them over here on the left side. And then we can write that one again. So 2 manganate, 6 protons, 5 peroxides. That goes to 2 manganese 2 plus, 8 waters, and 5 oxygens. And whenever we finish, we need to throw back on the states of matter that we've been leaving out. Manganate was an aqueous. Protons are aqueous because they have a charge. We said that hydrogen peroxide was aqueous. Manganese is aqueous because it has a charge. Water is a liquid. Oxygen is a gas. Here we are, just in the nick of time. We made it. That's what our balanced reaction looks like. We should have all of the same main components from the beginning. So H2O2, MnO4 minus, and on the other side, Mn2 plus and O2, plus coefficients, plus some extra features of the balancing, waters and protons. So now our second example, which is squished in here, says we need to balance the same reaction in base. And so the way that we balance things in base is we balance them in acid first, and then we tack on a couple of extra steps at the end. So let's rewrite our acid equation so it's workable. And then we'll continue on with steps 8 and 9 from there. Have to be careful in these problems because we really rely on our work in the very first few steps to give us the correct answer as we carry it all the way through the following steps. So you want to be careful not to make any addition or subtraction mistakes here. Okay, so we take our answer from acidic solution, then we're going to add in hydroxides to both sides of the equation equal to the number of protons. So our number of protons is here. 6H plus, so that means I'm going to add 6 hydroxides, not just to the left side, but to the right side as well. According to the rules of math, I can add or subtract whatever I like to both sides as long as I do it to the left and to the right. So I'm going to add 6 hydroxides to each side, and then according to rule number 9, that was rule number 8. Rule number 9 is that I can combine every hydroxide with a proton to give me a water. And in that way, we convert this solution from acid to base because we no longer have protons present, we have hydroxides present. So now we can go ahead and add those together and write that a little bit more cleanly. So now we've got 2 manganates, 6 waters, 5 peroxides. And on this side, we have 2 manganese ions, 8 waters. We now have 6 hydroxides as well, and 5 oxygens. We want to see if there are any terms that we can cancel. And I noticed that we have 6 waters on this side and 8 waters on that side. And so just like before, if we have 6 of something on one side and 8 of something on the other side, we can collect those all together and get 2 of that thing on the right side. And then we can write it again, clean it up. 2 MnO4 minus, the water is gone, 5 peroxide, goes to 2 manganese, 2 water, 6 hydroxide, and 5 oxygen. And if we're confident that we're finished, we need to go in and add those physical states, aqueous, 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 liquid, aqueous, and gas. So there is our balanced reaction in base. And if we compare it to our balanced reaction in acid, we should notice that all of the major terms are the same. And all of the coefficients in front of those major terms are the same as well. So in both cases, we have 2 MnO4 minus, we have 5 H2O2, we have 2 Mn2 plus, and we have 5 O2. Those numbers and those compounds should remain the same because all we've done is change the solution from acid to base. Nothing else about it has changed. So when you're doing this balance and you're changing from acid to base, the only things that should change should be your H2O, your H plus, and your OH minus. Those are the only things that will change with an acid to base rebalancing. If something else changed, you have probably copied it down. So we now know 3 ways to balance a reaction. We have the normal way, balancing a molecular equation. We have the special case for a net ionic equation when we can eliminate those duplicate ions on each side, those spectator ions. And we have a special way for redox that helps us to make sure we've balanced the charge on both sides. And so now we have learned all about the 3 reaction types. So we can go ahead and check off reaction types in our atoms first approach. So we are almost done learning about compounds. We have learned about moles and molarity, chemical equations and reaction types. All we have left are yield and limiting reagents and using that to describe macroscopic properties.